Welcome back, folks. I'm going to clean up a couple little things about current that I left out of the last video. Also make it a little more, make the videos a little shorter for you if I can. So let's revisit this drawing. It's a great drawing, isn't it? That's the height of my artistic ability. I feel so bad for you. So I said these were the electrons moving through this cross section, and that's certainly what's happening, but it doesn't always line up with how we analyze circuits. And this really dates back to when, at the dawn of our knowledge about electricity, the folks investigating that at the time, long time ago, centuries ago, knew that something was moving but didn't know what it was. We really didn't understand what an electron was back then. And they said something's moving, and we think it's moving that way. I got to check the camera to make sure I'm pointing the right way. That way, okay? And they said, okay, we're going to say it's going that way. And then once we figured out what an electron was and how the electrons were moving in relation to the electric field, it turns out the electrons were going that way. So we have this problem between the way electrons are moving and the way we say that the current is flowing. And we call these two opposing ideas conventional current, okay? And we call it conventional current because it's really just by convention. It's just the way that we chose to say it was flowing early on, and it's kind of stuck, and we've tried to change, and we can't. We're stuck with it. Conventional versus electron current. Okay, so if all of our negative charge is moving, in this case, to the right, okay, we could say that this is electron flow, okay, or electron current. Now, what we talk about more often than not is not the negative charge flowing that way, but the positive charge flowing that way. And positive charge is a little interesting because that's not what is actually moving. I usually do this on the desk with some props. I don't have my props with me, so I'm going to have to draw pictures. Oh, okay. So if we take a bunch of electrons, let's see how this works out. I haven't planned this. Shooting from the hip here. Okay, if we take a bunch of electrons and we line them up shoulder to shoulder, okay, next to each other. Okay, and then if I want to make the electrons flow, I can pull this one this direction. Okay, let's take a little time snap of what's going there. I'm going to pull it this direction. It's over there, right? And here I have this absence of an electron. Okay, it's a hole in the chain, if you will. Okay, and that's what we end up calling it. A hole. Okay. And that's our positive charge carrier. All right. It's actually the absence of an electron. It's not a real thing. It's just this figment of our imagination that makes our conventional current work out the way that we picked wrong all those years ago. I wasn't born, you weren't born. It's not our fault, but we're living with it. Okay? So as we make that hole, the electron's going to move. Oops. Okay, now that one's going to slide over here. Okay. And here's our hole. And we can continue this down this journey as we continue to slide our electrons. So I'm going to take that one, I'm going to move it over, and then I'm going to get 3 over here, and our hole is here, right? And then last one, as I move this to the right, our hole is going to be the first thing over here. Okay, and I've got 4 electrons, again, shoulder to shoulder over here. So in this example, that I usually do with props, but hopefully these pictures are working for you. The electrons are moving to the right. Okay, but look where the hole is going. I guess I started out with the hole here, right? The hole moves to the left. Okay, so it moves in the opposite direction. So it's, you know, we tried to change this in the 80s. I was alive in the 80s, but I wasn't studying electronics back then. And it didn't stick. Just sometimes convention takes a long time and a lot of effort to get rid of. So the electrons are flowing to the right, the holes are flowing to the left, and the holes are our conventional current. Okay, so our conventional current is actually flowing this way. Okay, conventional flow or current. Okay, so that was kind of the first thing that I wanted to talk about to clean up some concepts that we need for current in this class. But the other thing that I want to talk about is how we represent them as schematics. So for all of you MEs who have drawn one too many free body diagrams, how do we take a problem, abstract it in a way that we can apply some analysis methods and get the answers we want? So it's not a free body diagram, but we're going to draw a lot of schematics. And in drawing these schematics, we need to have a device that pushes this charge around for us. If we're in the classroom, I would usually go out and find a I'd walk over to the bench and I'd point to the device that I'm going to draw here. So our schematic symbol, okay, for a current supply one type is going to look like this, okay, and this is the one that I can usually walk over to the test bench and point to a what we call a power supply, and say this is your current supply. So this symbol represents this device, and it has a red post and a black post, and I can't quite do that here. Maybe I'll grab a picture of one in a moment, but this one is what we call an independent current supply. Okay, and I know it's an independent current supply because it's got the circle around it, and we'll look at what the other shape is in a moment, but it might have a part designation, so I'll say it's a current supply, so I sub S, and it may have some constant value next to it, so we would just say 2 milliamps. So it's going to push 2 thousandths of a coulomb per second, and the arrow is pointing up, and the arrow indicates, okay, that arrow indicates conventional flow. Conventional flow, okay? So the holes are going up, but the electrons are going down. You know, we're just going to use conventional flow. So at a point, you don't have to think about this. Holes are moving that way, electrons are moving that way. We can just say the current's going in that direction, and we're done. I want you to be aware of it because I don't want to give you half-truths. I don't think half-truths help you. So I don't know where you're going to go in your career. If you continue your study of electronics, the movement of holes and electrons becomes a little more important as you talk about semiconductors. So it is important to be aware that conventional flow is moving one way, the electrons are moving the other way. Okay, so I want you to be aware of that. But when we analyze circuits, we're really only interested in conventional flow, and the arrow on the current supply over there is indicating conventional flow. Okay, it's an independent current supply. It's independent of anything else going on in the circuit. This is the one that I can put in your hands. Actually, let me go grab you a picture of a current supply. I think I have one laying around. All right, I found it. Who's excited? Apparently me. So here's a picture of one of the ones from our lab that I happen to have because I started to make some posters, and it looks like that. I think we have some newer ones in that lab nowadays. But here's our current supply. All right. If I were to connect something to, now this one has multiple channels. So I'm trying to see if this is channel 1 or channel 2. I can't see a designation, but I'd imagine it's channel 1. This red post corresponds to the top here. Okay, this black post corresponds to the bottom over here. The green post is ground. We'll talk about what ground means. This is a chassis ground, and it's not necessary when we're doing experiments in the lab that often, but it has a very particular meaning. The red post is the top, the black post is the bottom. So conventional current is going to flow out of the red and into the black, and then we can set these knobs, and we set them correctly, we end up with a current supply. So I could set this to be a regulated 2 milliamp current supply by setting the current value here and then giving it more voltage than it needs. Okay, just enough voltage that it can push the amount of current it needs to. And this is a physical thing. So this one's a little easier. The circle is a little easier because it's a physical thing that I can point to. I can have you hook up wires. I can have you hook up components and measure the current flowing through it. The one that kind of throws people a little bit because it's not a physical component, it's a component that we use to model other components, is the dependent current supply. Okay, so let me fit that in down here. Okay, and our dependent current supply looks like this. Okay, it's going to have the same arrow indicating current flow, and it is going to be conventional flow again, but it's going to be a diamond. Okay, do not be scared of diamonds. Okay, the value of current, the amount of current flowing out of the top post of this dependent current supply is dependent on a value somewhere else in the circuit. So it's a current flowing out of here. It's always a current. I'm looking at the symbol inside. I'm going to say this is a current supply. But it can be dependent on another current, or it can be dependent on a voltage somewhere else in the circuit. Okay, so we might see this one labeled, we might similarly see it called IS because it still is a current supply. But we might see its value labeled as 4Vx. Okay, and Vx has to be defined somewhere else in the schematic so that we can go find Vx, multiply it by 4, and that's going to tell me how much current's flowing through this current supply. Okay, we usually use this this dependent type of source when we're modeling amplifiers of some sort. So operational amplifiers, if you've dealt with them in some of your other classes, some of you have probably taken classes that deal with those, some of you have not. As you go study semiconductors, we might model a semiconductor using a dependent current supply like this one. If for you Emmys in the room, if you're going to go talk about control systems, there was a time where we implemented control systems using analog components, and some may still be implemented using analog components. But if you want to measure a value, multiply it by a gain, and then feed it back into the system, a transistor and amplifier is a wonderful way to do that. And we might model that that type of behavior using a dependent current supply. So it looks just like this one here. So a circle up top, whoop, up top there, just peeking out, is independent, and the diamond down here is dependent. And this is how we'll represent devices that push current in some kind of regulated fashion through the circuit. Okay, some of them are physical, and some of them are more theoretical. Okay, so that was what I wanted to clean up with current. And if we want to make these electrons move, or the holes move, now that we have a positive charge carrier we can talk about, then we have to push them. Okay, all we're doing is pushing electrons here, and if we're going to push them, then we have to talk about what force we're pushing them with. So maybe you already know what that is. If you don't, go click on the next video. All right, so stay tuned and good luck. And now I'm big. Woo! Wrong button. Okay.